Okay. Right. So we'll do an example or two of the concept of constraint relations by virtual work method. Okay. So we'll start with a few applications of this first. Okay, so this is a system of two massless pulleys and also two blocks like this in a vertical situation. So pulleys P1 and P2 are massless. Okay. Both the threads used, obviously massless and also smooth, no friction involved. Both the threads used, this thread here and the second thread going around pulley P1, are also massless and inextensible. Okay. So suppose mass of A is 15 kilograms, mass of B is 10 kilograms, and G is 10 meters per second square. Find the accelerations of A and B. Similar type of question we've done in the last lecture. Okay, so just try this out. So you know what to do in this question. First, make the constraint relation for the relationship between acceleration of A and acceleration of B, and then write the free body diagram equations, and you should be able to solve this. Yeah, I'll be explaining virtual work concept, don't worry. Okay, Samarth, you have to tell me which one is going up and which one is coming down. Tell me the directions also. You given me the magnitude of accelerations. What about the direction? No, unfortunately not correct. So that means your direction has to be opposite now, what you've considered. So you have written your equations assuming something, some particular direction, that B is going up and A is coming down or whatever. So if you're getting acceleration is negative, then the actual acceleration is opposite of that. Okay. So let's start with the constraint relation. So if I assume, now actually it's quite easy to determine the direction of acceleration. You can see that mass of A being 15 kg and mass of B being 10 kg. Now before you start with the constraint thing, you can see that if the tension in this string is T, then the tension in the second string is becoming how much? It's becoming 2T. Okay. So you can see that on the block A, the total tension acting is 2T and you have weight. And on the block B, sorry, is 2T plus T, 3T. Okay. And on the block B, okay. So you can understand here that for equilibrium condition, okay, weight of A should have been 3 times the weight of B. So therefore you understand, if mass of A is less than 3 times mass of B, what will happen is the block A will accelerate upwards, the block B will accelerate downwards. So logically only we can understand this. अरे see the diagram है ना, T plus 2T कितना होता है? 3T होता है. Yes, Smith. What happened? This is not clear. This is the same as the last question we did previous lecture. Only the values are different. Okay. Okay. So now you can understand that in this diagram, if E goes up by a certain amount, let's say x1, then this pulley will come down by the same amount x1. Okay. So what is happening? How much thread is getting released? From here, the thread getting released is x1 plus x1 plus x1. 3x1 amount of thread is getting released. So x2 has to be 3x1. So see, if you just analyze just this portion. Okay. Now what is happening? This is reaching here. So x1 amount of thread is getting released here, and this is coming down by x1. So another x1 amount of thread is getting released. So the length of the thread is decreasing by 3x1. So here it has to increase by x2 such that the length remains constant. Okay. So this is what tells us that x2 is equal to 3x1. So that's your constraint relation for displacement. Shikhar, it is 2t in that thread because this pulley has to have net tension equal to 0. You people are not revising what is done in the previous lecture. If this tension is some T2 and this tension is some T1, the pulley is massless. Discussed in a lot of detail. I made you note down these points in the last lecture. I've asked you many times to make it a point to please revise what we do in the lecture notes first and foremost. Okay. Now look at this diagram where I've just concentrated on the pulley P1 and the thread joining that with A and B. So what is happening? The pulley is coming down by x1. So कितना thread release हो रहा है? 2x1. But ये side में the block A is also going up by x1 ना? So another x1 amount of thread is getting released. So the thread length is decreasing by how much? 3x1. So on this side when B comes down by x2, it has to increase by x2 such that these two compensate for each other. The thread length remains constant. Following this now, constraint relation is clear? Okay. So once you have this constraint relation, from that you will get the relation for the accelerations. Okay. So acceleration of A is to acceleration of B will become 1 is to 3 because displacement of A is to displacement of B is 1 is to 3. So the downward acceleration of B is 3 times the upward acceleration of A. This is our first equation. Rest you can see the free body diagrams. In inertial frame, so these are my equations. Okay. Now to solve them, I can do like this. Divide this whole equation by 3. Okay. And the third equation, add these two. So approximately you have values like this. Okay, so I was expecting more people to get this because this is a repeat of what we did in the last lecture. So people are not revising things done in the last lecture properly. That is the bare minimum you have to do here. You have to revise every lecture properly. So anyway, note this down, make sure every point is clear. Now next we'll discuss an alternate method of the constraint relation, which is called the virtual work method. Okay, next up we will discuss an alternate way of constraint relations. It's very important for your entire mechanics, actually, not just for Newton's laws, but for entire mechanics. So virtual work, or later stage we'll also understand virtual power. Okay. For constraint relations. So the statement of the theorem is like this, that for any system in a state of motion, okay, the net work done by internal forces such as tension in a thread, string, etc., or normal contact force between two bodies in the system. Okay. So the net work done by these sort of internal forces is always equal to zero. Okay. This is the statement of the virtual work theorem. Okay, make a note of this statement first. Obviously, you know that aside from this, the definition of work done by a force F over a displacement S is given by the formula F dot S. So this is something that you know aside from this. So if you have a body on which you're applying a force like this, but the displacement of the body is like this, it's moving from there to there. So during this displacement, this will be the work done. Okay. So note down this theorem first, then I'll start explaining it in context of Newton's laws problems. Make sure you write down the statement and the explanation properly, because this is not um, usually described very well in reference books. Okay, just the method is used while solving problems, but the logic of the method is not always explained so well. So make sure you have written it down in detail and properly in your class notes. Of course, I will be sending you these notes also, but Okay, so written down the statement. I hope this is clear. Okay. Now let us see this in action in certain examples. So let's see how exactly this works out. No, we have not started work energy theorem. Work power energy chapter will start much later after friction and all that. Okay. Okay, yes, Smith, but write down quickly. Shikhar, first do this theorem, okay? Then we'll see about your confusion. Because otherwise we get sidetracked. We're trying to learn one thing over here. You can always go back to your notes and clear that confusion, yeah? Like you've done n number of problems related to inclined plane. So there's nothing to get confused over there. That's why I'm saying that you should have completed HC Verma by now. If you've done all those problems, then you would not have these confusions. Okay, let's see a basic example. So we have this frictionless surface. And we have these two blocks which are attached by a thread. And now what we are doing is we are applying some kind of external force. Like this. So that sets off the system into motion. Okay. Now we're not concerned with solving this problem fully, but what we want to just show is that if we take this whole thing as a system, we take our system as the block A plus the block B plus the thread, then what is happening? Tension T, it is becoming an internal force within the system. Why is becoming an internal force? Because there's no external agent applying it. The tension acting on A is applied by the string on the block A. So the thread and the string and the block A are both part of my system. The tension acting on block B are again acting between the block B and the thread, both of which are part of my system. So it's not applied by some external agent, but applied internally. Okay. So it is not being applied by any external agent, but rather it is acting within the system. So it's an internal force. So therefore, the net work done by tension should be zero. So let's verify that. Okay. So how to verify that now? Let's say initially this was what the system was like. Okay. This is at some time t. Now after some time, let's say this is what has happened. Continuously applying this force, or maybe after some time you stop applying it, it doesn't really matter. But this is where the system is at t plus delta t. Okay. So A has had a displacement like this, B has had a displacement like this, and you can see that because the thread length remains conserved, the displacement of A must be equal to the displacement B because of thread of constant length between them. Okay, so now if you consider on the block E, tension ऐसे act कर रहा है and E is having a displacement like this. If you consider the block B, tension is acting like this and the block B is having a displacement like this. So work done by tension on block E कितना होना चाहिए? Should be plus T into SA, because you can see they are parallel vectors. But similarly, the work done by tension on block B वो कितना होना चाहिए? Should be minus T into SB, because these two are at 180 degrees angle. Okay, so that's why. Okay, so net work done by tension, which is work done on block A plus work done on block B, should be 0. So that means okay, so that means that SA, okay, so that just confirms this. Okay. Which you already know. Okay. So this is the working of the virtual work concept in this particular question. It's not really giving us any new information, but I'm just explaining how it works. Now we will see how to use it in a more complicated problem to get constraint relation and all that. But I'm just first, let's get used to the theorem itself. Let's understand how it works in a situation like this. No, tension in the string is same as proved by free body diagram method earlier. Rather, you can say what this proves is that if the string is inextensible, then E and B should have the same magnitude of displacement, same magnitude, and in this case, the same direction of displacement also. So you're proving that thing as a constraint, that SA should be equal to SB. So if you double differentiate that, acceleration of A should be equal in magnitude to acceleration of B. That's the only thing you end up proving over here, which is obvious anyway because there's no system of pulleys here. So it was a very obvious thing that they had same magnitude of acceleration. In this case, same direction also. Okay, now let us see the working of this in another situation. स्ट्रिंग में टेंशन यूनिफॉर्म रहेगा वो तो पहले से वी हैव सीन बिकॉज इट्स massless string. It just proves that here the accelerations will be same because displacements are the same. Proves this also. So they will have common acceleration. Okay, Shikhar, done with this? Okay. Now let's see another trivial case, simple case. Then we move on to the system of pulley cases. Another example. Let's take the case of the simple Atwood machine. Okay, and let's say A is heavier than B. So what we'll say that after some time, the block A displaces downwards and block B displaces upwards. Now you can see that the magnitude of this one's displacement will be equal to the magnitude of this one's displacement. Okay, but the tension acting on both of them is of same magnitude. So you can see that tension is acting at 4 places. Okay, but on the pulley, tension is acting at 2 places where the work done is zero here because the displacement is zero. But on the block E, the tension is acting like this and the displacement of E is like this. So work done on E is minus T into SA, and the work done on B similarly will be plus, it will be a positive quantity. So B displaces like this after some time, A displaces like this after some time. So work done by tension on B will be plus TSB. So now when you see the net work done by tension within the system should be zero. Okay. So here we are taking a system as the blocks A and B plus the thread plus the pulley. This we are taking as a system. Okay. So tension is an internal force within the system here. Okay. So that's why this net work done should be zero. So again, so SA should be the same magnitude as SB. Okay. Therefore, the acceleration of A has the same magnitude of the acceleration as B. So they will be having the common magnitude of acceleration. So make a quick note of this. Again, this is not giving us any new information. We already know this. I'm just showing you the working of the virtual work method. And the virtual work theorem, this is the statement of it. No, not in simple Atwood machine. That is the whole point. In simple Atwood machine, the displacements of A and B have the same magnitude. If you want different displacements, you have to create a system of pulleys. Okay, now let us come to something where there is a bit more of complication in the form of system of pulleys. Okay, write down fast so. No, Samarth, I'm just doing it for fun. It doesn't make life really simpler for us. I'm just teaching it because I like to teach things which are fun. Otherwise, this has no relation. Okay, to anything we are trying to do. No, I'm not giving you the masses of the blocks in that problem. So how you will find the accelerations? You understanding? I told you the only thing I'm doing in that problem over there is to explain the working of the virtual work theorem. Why the net work done by tension within the system will be zero. That was the only point of that question. Okay. Anyway, now start taking down this diagram. So both pulleys are massless and the thread used is massless and also inextensible. Okay. So find the ratio of these accelerations. We know that these will tend to accelerate like this because there's a smooth surface. So gravity acting on M2 downwards. So you want to find the ratio of these accelerations. So you know the ratio of the acceleration is 2:1. That's correct, Viraj. Okay. But now what we will do is we will find that ratio of accelerations using virtual work method. Okay. So in this same problem now, we will see how virtual work method gives us a very easy way of solving the problem without considering thread length and all that complication. So what is happening here is after some time, if the block A makes a displacement of S1 like this, okay, and during that time, this makes a displacement of S2. Okay. So this is at T plus delta T. As the original diagram was at time T. Okay. So you can see that on the block M1, the tension acting is only T, whereas on the block M2, the tension acting is 2T. So on M1, there's a tension T acting like this, and it makes a displacement of S1 to reach here. Whereas on the block M2, now I'm not worried about other forces, I'm just talking about tension. So how much tension is acting? 2T, and it is making a downward displacement during that time and reaching here. So again, the net work done by tension should be zero, because again we are considering our system as the blocks M1 and M2 plus both the pulleys plus the thread. So tension is an internal force. Okay. So work done by tension should be 0. So work done by tension on block 1 is plus TS1, but on block 2 is minus 2TS2. So from this you can see that S1 is twice of S2. So this is the constraint relation. So this is the other way of calculating the constraint relation using the work theorem. Yes, definitely. Especially in more complicated system where there are multiple threads, not just one thread, but more number of threads, the virtual work theorem is going to be much easier. You have to determine the direction of acceleration. Okay, now let us see the next example, very similar to the example we did earlier today. In fact, that example only, let's determine the constraint relation by virtual power method, or virtual work method rather. So we had this kind of system. So the pulleys were massless and all. So because of the pulleys being massless, we saw that the tension in the second thread became double of the tension in the first thread. Okay. So now you can see that suppose A is going up and B is coming down. You can see that on the block A, the total tension acting is 3T and it is having an upward displacement. Whereas on the block B, the tension acting is T, but it is having a downward displacement. So again, considering our system as both blocks plus pulleys plus both the threads. Okay. So we have plus 3T into SA minus T into SB is 0. So acceleration of A, so this becomes very easy. So particularly in a system where there are multiple threads and it's a little difficult to use the conservation of thread length, it's a bit lengthy. Okay, the virtual work method becomes very useful. Okay, so hope this is clear to you. So next we will do a numerical example where you will see the advantage of using the virtual work method. All right, Amay, but write down fast. Okay. Okay, so we just have one more added pulley compared to last one. So this pulley P1 is attached to a fixed wall, I mean fixed ceiling, but P2 and P3 are attached to threads like this. Okay. Okay. So let's work out this question next. So mass of A is 15 kgs again. Mass of B is 5 kgs. Okay. And G is like this. All the three pulleys are massless pulleys. And the threads are massless and inextensible. Okay. So first of all, determine the directions in which A and B will accelerate. Okay. And then determine the ratio of their accelerations, and then from that determine their accelerations itself in meters per second square. Just check your answer not correct, Priyank. Maybe some calculation mistake. Okay, just check your answer for the ratio. So just try this question out, people. Okay, so you should be getting the ratio of the accelerations as 1:7, okay, in this case. But first of all, let us understand what is happening here. You will see that once again, even though A's mass is 3 times, A will be going up and B will be coming down. Okay, so that's pretty easy to understand directly from the diagram itself. Okay, so first of all, if you see in this diagram, if the tension in this thread is T, then the tension in this second thread here will become 2T. Okay, and then in this, on this pulley, the net force has to be 0. So this tension has to balance these two. So it has to be 4T. Okay, so it's like if you take this tension as T1, this tension T2 is twice of that, and this tension T3 becomes like this. Okay, so now if you look at the individual free body diagrams of A and B, you will see that on the block E, the tension acting is T3, which is 4T, plus T2, which is 2T, plus T1, which is T. So the total tension acting upwards is 7T on A. And on the block B, on the other hand, the tension acting is T. Okay. So therefore, you can also see that for equilibrium, this is the condition for equilibrium. Okay. So therefore, you can see that if mass of A is less than 7 times mass of B, that means that A will accelerate upwards and B will accelerate downwards. If mass of A is greater than 7 times mass of B, then A will accelerate downwards and B will accelerate upwards. So this is the, you can say, the first part solution. Then we'll also apply virtual work and get the ratio of accelerations, the second part. Because specifically I've taken the masses to be 15 and 5 here, so you can see. Okay. So the mass of A is only 3 times the mass of B. Or it is less than the required 7 times mass of B. So this situation is happening. नहीं, G से ज़्यादा नहीं हो सकता बेटा. Yes, Smith, you cannot get an acceleration of more than 10 meters per second square, more than G. Both of them have to have accelerations of less than G. But in the ratio 1:7. Okay, so just check your calculations. Okay, so now additionally in this diagram, we know that because of these masses taken 15 and 5, E will be accelerating upwards, B will be accelerating downwards. So apart from this, we also know that okay, so let us move on now to the constraint relation, second part of the question. So from the first part, we have been able to understand this much, that block A is accelerating upwards and block B is accelerating downwards. Now we apply the virtual work concept, that on A, the tension acting is 7T, and on B, on the other side, the tension acting is T, but A is making a displacement in the upward direction. B is making a displacement in the downward direction. So taking a system as both blocks plus all three pulleys plus all three threads. Okay. The net work done by tension should be 0. So on E, the work done by tension is plus 7T, and on B, the work done is minus T into SB. Whereas everywhere else, the work done by tension is 0. Okay, so one more thing you can see here, that if you look at the pulley P2, for example, okay, so on this pulley, you can see that net force due to tension is 0. So therefore, work done by tension is 0. So on pulley P1 and rather P2 and P3 and also P1, the tension is not doing any work. Okay, so the net work done is only the work done on A plus the work done on B. So you can see that SA is to SB will become over here 1 is to 7. So differentiate that, and the ratio of the accelerations of A is to B will be 1 is to 7. So you can try this later by the thread length method yourself, and you will see it's very lengthy by thread length method. If you go to conserve the thread length and prove that the ratio of displacements is 1 is to 7, therefore the ratio of accelerations is 1 is to 7, you will get the answer, but you will end up you'll have to conserve 3 separate threads lengths and 2 moving pulleys along with 2 moving blocks. So the whole thing becomes quite complicated. Okay, so now come to the third part. In the third part, just solve the free body diagram equations. Okay. So for the third part, your this thing, take this as equation 1, okay, and solve the free body diagrams. Okay, and from that determine the accelerations. So the free body diagrams that you make them in inertial frame, okay, in ground frame only. So there's no pseudo force or anything like that. Okay, so constraint relation is clear to all of you, I hope. Now let's come to the free body diagram equations. Yes, Devash, your answer is correct, I think. Okay. So this is my second equation. Whereas on the other block, 5g, this is having a downward acceleration of EB. So we have 5g minus t is equal to 5 times acceleration of B. So that is the third equation. Okay. So now it's a matter of solving these equations. So to solve, what you can do is you can first substitute from equation 1. So this equation becomes this. Okay. Then what you do is when you compare it with this equation, you see that this equation has 7t and this has t. So you multiply this with 7. Okay. And then compare it with this equation. This is equation 2. Now you can add these two equations. So the moment you add, what happens is your 7t cancels out. But you have 35 minus 15 g is equal to, this will become how much? Yeah. So this becomes your final answer. So 10 by 13 and 70 by 13, or simply g by 13 and 7g by 13. These are the accelerations. To eliminate t, this process here, is solving simultaneous equation. No? But if you're solving for acceleration, then you have to eliminate the other variable of tension. So this is pretty basic math stuff. Solving of simultaneous equations, something you've been doing from class 8, I hope. So no, we are adding the two equations, beta. We are not subtracting the two equations. Look closely at what we've done, you will understand. ये तो सिर्फ algebra है बेटा, आपको दोनों equation add करना है सिर्फ. I've clearly explained in that step what I've done. Anyway, so I hope all the equations are clear now. See, this has minus t and this has plus 7t. So that's why we are multiplying this by 7 and adding the two equations so that that 7t term gets cancelled. Okay, next example for you to solve yourself. Okay, so I hope this example is clear to all of you. So we have this pulley attached like this. So we have a combination of three blocks like this. Okay. All surfaces are smooth. And this is a massless, inextensible string. Okay. Now, also given to us that this inclined plane here is at an angle of 30 degrees with the horizontal like this. Okay. All pulleys are also massless and smooth. So if the mass of all three blocks is the same, show their direction of motions, and the constraint relation between the magnitude of A's acceleration, the magnitude of B's acceleration, and the magnitude of C's acceleration. And second part, find these accelerations. Take G as 10 meters per second square. So just try this out. This is actually easier version, easier question, but with the application of that thread length conservation constraint that we were discussing. Yes, very good. Samar, that is correct. Nee, Sujal, here it will not be in terms of ratio, and it will be like a linear equation. So anyway, what we'll understand is that this block will be sliding down the inclined plane. This will be sliding along the horizontal, and this will be accelerated downwards. Okay, and there is the same magnitude of tension acting everywhere. Okay. So now if you look at the individual free body diagrams, you will understand that for the block A, tension is acting like this, mg is acting like this, normal reaction is acting like this angle is theta. Okay. For the block C, normal reaction like this. Okay. And for the block B, so now you can see that from the virtual work method, plus t into displacement of A minus 2t into displacement of B plus t into displacement of C should be 0. So you can see that in this diagram, A will make a displacement along this direction, C will make a displacement along this direction, but B will make a displacement opposite to tension. So this is a constraint relation. This is our equation 1, and this is also the solution of the first part. No, but tension is also acting along the negative x-axis. Tension and displacement are parallel. So the work done on C is positive, Samarth. That you can clearly see in this diagram I made. Yes, it is incorrect. It is acceleration of A plus acceleration of C, which is acceleration of B. कैसे इक्विलिब्रियम में बेटा? फ्रिक्शन है ही नहीं, सारे सरफेसेस स्मूथ है, तो बी के वेट की वजह से वो नीचे खींच रहा है ना, तो कैसे इक्विलिब्रियम में रहेगा? Okay. Now you write the FBD equations. So FBD equation for the block A, okay. Now resolve the weight into components. So this is mg cos theta, this is mg sin theta. Okay. Then there is normal reaction and tension, and it's having an acceleration in this direction. So for the block A, we have the equation P plus mg sin theta is this. Okay. Then for the block B, so already seen the equation mg minus 2t is equal to mass into acceleration of P. Okay. And for the block C, you just have one horizontal force, that is your fourth equation. Okay. So one thing you can do here, which will be very convenient, is that if you just add the equations 2 plus 3 plus 4, it gets rid of t. See, t minus 2t, so you get mg 1 plus sine theta is equal to m into acceleration of A plus acceleration of B plus acceleration of C. So you get the relation that put sine theta as half. Okay, so you get this relation. Now in this, what you do is you substitute from this, substitute acceleration of A plus acceleration of C as 2 times acceleration of B. So on doing that substitution, you'll get 3 times acceleration of B. So acceleration of B comes out to be g by 2. Okay. Then substitute this in equation 3. Achha, write down up to here first. Okay. Then what you do is you substitute this in equation 3. So you'll get mg minus 2t is m into g by 2. So from that you'll get tension as mg by 4. Okay. So now substitute that in equation 4. So you'll get acceleration of C as g by 4 and you'll get acceleration of A as 3g by 4. Okay. So finally, these are the answers you'll get. Solving the system of equations, you'll get acceleration of B is g by 2 downwards. Acceleration of A will be 3g by 4 down the inclined plane, and acceleration of C will be g by 4. Okay, so this is the complete solution of this question. No, tension will come mg by 4. Tension is mg by 4, beta. Tension has to have the dimension of force. It doesn't have the dimension of acceleration. M is the common mass of all three, given in the question that masses are same. Okay, so hope this question is clear to all of you. All right, so with this we conclude the lecture. Okay, now please, once again I'm saying complete each and every question from H.C. Verma, Newton's Laws chapter. And if you have any doubts, please let me know. And start working out questions from the module also. Module exercise 1, 2, etc. Okay. That's it for today's lecture, people. But make sure you're working out questions from H.C. Verma as well as the module.